Imagine your most sensitive digital secrets, the encryption keys that guard everything from your online banking to your personal messages. You probably think they're safe from, clever software hacks or maybe brute force code breaking attempts. But what if those secrets could be stolen by something far more subtle, almost imperceptible? Something like the tiny fluctuations in the power your smartphone draws, or the minute electromagnetic waves it emits as its internal chips process data. That's the unsettling reality of what we call side channel attacks. It's like a whisper in the machine that can betray everything you thought was secure.
Precisely. We often default to thinking of cybersecurity as this purely digital battle, right? Fought solely with algorithms and lines of code. But what's truly profound here is how the physical implementation of cryptographic algorithms, the way they're designed and run on actual silicon microchips, introduces an entirely new, often incredibly vulnerable attack surface. These physical leakages, these whispers you mentioned, they create a unique signature that an adversary can intercept and analyze. And surprisingly, that signature could betray the very keys meant to protect our most sensitive digital information.
And that's exactly what we're embarking on today in this deep dive. We're exploring a truly innovative new approach designed to make these critical encryption processes virtually invisible to such physical attacks, achieving what the researchers describe as unprecedented levels of security. We're going to unpack an impressive piece of research from a collaborative team at Purdue University, Georgia Institute of Technology, Intel, and Intel Labs. Their paper, titled EM and Power SCA Resilient AES 256 in 65 nm CMOS, through 350 current domain signature attenuation, describes an innovation that fundamentally rethinks how we protect our digital world at its very core. So let's begin by grounding ourselves in the basics for anyone new to this concept. You might be wondering, what exactly is a side channel attack? Because it's not what most people imagine when they think of hacking. This isn't about directly cracking the encryption algorithm itself, trying to guess the code through mathematical means like brute forcing a password. Instead, it's about observing the side effects of the computation. Think of it like this. Imagine trying to figure out what someone is doing inside a closed, soundproof room. You can't hear their words, you can't see what they're doing, but you might be able to detect subtle clues from outside. Maybe the sound of their footsteps as they move, or the soft hum of an appliance they turn on, or even a tiny fluctuation in the lights when a powerful device draws current. Side-channel attacks exploit these kinds of physical information leakages, like variations in power consumption, or the subtle electromagnetic emanations a chip radiates, rather than attempting to break the encryption algorithm's mathematical strength.
That analogy perfectly captures the essence. To get a bit more technical, when a cryptographic algorithm, such as the Advanced Encryption Standard, or AES 256, which is a widely used symmetric encryption algorithm, processing data in 256-bit blocks handles sensitive information like a secret key on a physical microchip. The precise sequence of operations performed at the fundamental transistor level can vary ever so slightly. These variations depend directly on the specific bits of the key being processed. What's truly fascinating here is that these tiny key-dependent differences in computation translate into equally subtle but measurably distinct differences in the chip's power usage, the current it draws from its power supply, or in the electromagnetic waves it radiates into the surrounding environment. The paper explicitly states that these are critical physical signals correlated with the secret key.
So the leakage isn't random, it actually relates to the secret.
Exactly. An adversary equipped with specialized, often off-the-shelf equipment can then analyze these patterns over many operations to reconstruct the secret key byte by byte. And they can do this even if the algorithm itself is mathematically considered secure. The strength of the crypto algorithm is irrelevant if its physical implementation leaks information.
Okay, so these physical whispers are very real, and they expose a vulnerability we might not typically think about. But what does this all truly mean for you, the listener? Why should you, as someone perhaps using a smartphone, making online purchases, or relying on secure communications, care about these almost imperceptible fluctuations?
Well, the reason is precisely because these attacks are so insidious and powerful.
Right.
They don't try to solve the encryption puzzle. They simply observe the process from the outside, entirely circumventing the mathematical strength of the encryption algorithm.
Right.
This makes them incredibly dangerous because they can affect secure hardware and practically everything we use.
Like what sort of things?
Oh, from your personal smartphone and tablet to the credit card readers at your local store, the hardware security modules protecting vast amounts of data in cloud infrastructure, and even critical embedded systems in modern cars, medical devices, or industrial control systems. It's a very real and present danger to personal privacy and the integrity of our digital data, often without us ever realizing our secrets are being silently observed or extracted.
Wow, that really broadens the scope. It's not just about high-end espionage then.
Not at all. And this raises a profoundly important question. If the physical implementation of our secure hardware, which is the very foundation upon which we build our digital trust, is vulnerable to such subtle observations, how robust can our digital security truly be? It fundamentally underscores the fact that cybersecurity isn't just about software updates, firewalls, and complex algorithms. It's deeply entwined with the physics of the hardware running those systems.
So the hardware itself is part of the attack surface?
Absolutely. The implications are immense. Consider secure elements embedded in smart cards, which are used for everything from payments to identity. Think of the vast array of Internet of Things, or IoT devices, from smart home gadgets to industrial sensors, all of which increasingly rely on on-chip cryptography to function securely and privately. Or even advanced automotive electronics, where the integrity of encrypted communications is paramount for safety and security. If these foundational components can be compromised via side channels, the entire chain of trust can break down, potentially leading to widespread data breaches or even physical system compromises.
So if this is such a significant threat, you might be thinking, surely engineers have been working on this for a while, right? This isn't a brand new revelation. What have they tried before, and why haven't those solutions been enough?
That's an excellent point, and you're absolutely correct. The research paper we're discussing explicitly outlines several prior circuit-level on-chip countermeasures that have been developed and deployed over the years to try and mitigate these side-channel attacks. These efforts were highly sophisticated, involving techniques like switched capacitor current equalizers.
Okay, trying to smooth things out.
Exactly. They attempt to smooth out power fluctuations by rapidly switching capacitors. Other approaches included charge recovery logic, designed to reduce power variations by reusing electrical charge, or integrated voltage regulators, IVRs, and all-digital low-dropout LDO regulators. These try to provide a very stable power supply to the cryptographic core.
So quite a few different strategies then.
Yes, but when we look at the broader picture, these methods, while well-intentioned, often suffered from significant and sometimes debilitating drawbacks. Firstly, they frequently led to noticeable performance degradation, meaning the chips ran slower.
Always a trade-off.
Often, yes. Secondly, they often required substantial power consumption and large silicon area overheads because they necessitated incorporating bulky embedded passives like large capacitors and inductors directly onto the chip. This increased manufacturing costs and chip size. But here's the truly critical point, almost a whack-a-mole problem. These prior solutions could inadvertently introduce new leakage paths. For instance, those large metal insulator metal, or MIM capacitors that might be part of these countermeasures, especially their top metal plates, can themselves act as tiny antennas radiating key correlated electromagnetic information.
So fixing the power leak creates an EM leak.
Potentially, yes. A design might successfully smooth out power consumption, only for the very components doing that work to become a new source of EM leakage. In essence, they might plug one leak, but due to their physical nature and design, inadvertently create another, sometimes making the system less secure or less practical than intended. It's a continuous, complex game of cat and mouse in hardware security, with each fix often revealing a new challenge. This particular research paper focused on a chip fabricated using 65-nanometer CMOS technology. CMOS is complementary metal oxide semiconductor, the basic tech, and 65mm is the feature size, how small the transistors are. It's a common technology, so the findings are pretty broadly applicable.
So we've established the serious vulnerabilities of side-channel attacks and how previous attempts at fixes often created new headaches or introduced performance trade-offs. This paints a challenging picture. What was the breakthrough insight, the novel concept that allowed this team to fundamentally rethink the problem and move beyond those old limitations?
This is where the innovation truly shines. What's profoundly insightful here is the team's recognition that the correlated current, that tiny fluctuating electrical signal carrying the secret key information, is the common root source of both power leakage, which you can measure at the supply pin of the chip,
Right.
and electromagnetic leakage, which radiates throughout the current's path within the chip itself.
Yeah.
The core innovation, current domain signature attenuation, or CDSA, embraces this fundamental understanding. Its primary goal isn't just to mask the symptoms, it's to make the supply current drawn by the cryptographic engine almost perfectly constant, essentially making it independent of the actual variable current drawn by the AES encryption engine as it processes sensitive data.
Almost constant.
Almost perfectly, yes. This isn't about simply hiding the secret better. It's about fundamentally altering the current signature so that there's simply no key correlated information left to observe in the chip's external power supply or its overall electromagnetic emissions. The paper clearly describes CDSA as a low-overhead generic countermeasure designed to combat both EM and power side channel attacks simultaneously. It's an elegant solution that tackles two critical problems with one integrated approach.
So, if I'm understanding correctly, the core insight here isn't just to hide the secret better, but to make the very act of doing encryption virtually undetectable by external observers in terms of its current draw and EM radiation. That's the real game changer, shifting from trying to obscure the signal to virtually eliminating it from the outside world.
Exactly. It's a fundamental paradigm shift in how we approach hardware security at this level.
Imagine for a moment a cryptographic engine that, from the outside, appears to be doing nothing at all, at least in terms of its current draw. It's like watching a perfectly stable light bulb that never flickers, whether it's encrypting a top-secret message or just idling. By cleverly embedding the cryptographic engine within the CDSA circuit, the authors achieve precisely this. The supply current becomes almost perfectly constant, truly independent of the AES current, effectively rendering it invisible. You can even see this depicted in Figure 27.3.1 of their paper, showing an incredibly flat, unrevealing current profile. But what does achieving this near-perfectly constant current really mean for security? What's the single biggest takeaway for our listeners about what this implies?
This achievement of a near-constant supply current has a profound, indeed dramatic effect on our security metrics. The single biggest takeaway is that it makes side-channel attacks practically impossible by dramatically increasing the minimum traces to disclosure, or MTD.
MTD. Okay, remind us what that is again.
Sure. MTD is the number of cryptographic operations or traces, those individual observations of power or EM fluctuations, an attacker needs to collect to successfully recover the secret key. A higher MTD value means the system is exponentially more secure, requiring vastly more effort and time from an attacker, potentially making an attack entirely infeasible in a practical sense.
Got it. More traces needed, much harder attack.
Precisely. Specifically, for power side channel attacks, the MTD increases by a factor equivalent to the square of the attenuation factor achieved by CDSA. So the 350x attenuation of the current fluctuation means a massive increase in MTD. A squared increase.
Wow, squared, that's huge.
It is. Furthermore, this constant current also drastically improves EM-SCA MTD because the current flowing through higher-level radiating structures, like the pins on the chip package or the traces on the circuit board, is now nearly constant. This uniformity prevents any key correlated radiation from escaping. The paper proudly reports achieving the highest minimum traces to disclosure, MTD1B reported to date, which means over 1 billion traces were not enough to break it. That's an absolutely incredible benchmark in the field of hardware security, moving the goalposts so far that current attack methodologies simply cannot keep up.
Okay, that all sounds like pure magic on a conceptual level. But now let's pull back the curtain on the actual electronics. How do they achieve this constant current wizardry with such incredible precision? What's going on under the hood of this innovation that allows it to effectively silence these whispers?
It's certainly a testament to clever, meticulous circuit design. The CDSA circuit fundamentally relies on a digitally tunable cascode current source, or CS, which possesses an exceptionally high output impedance. A cascode, for those perhaps less familiar, is a circuit configuration designed to increase an amplifier's input or output impedance and bandwidth, making it incredibly effective at maintaining a stable current even if the load it's supplying changes.
High impedance means it resists changes in current flow.
Exactly. This specialized current source is directly responsible for powering the AES core itself. The ingenious goal of this circuit isn't just to provide the average current that the AES needs to operate. It also provides a carefully controlled delta current that then bleeds through a bypass PMOS path to ground. PMOS, p-channel metal oxide semiconductor, is a type of transistor. This bleed path is crucial because it provides a local negative feedback mechanism. This enables analog regulation of the current without the need for a high-power shunt loop, which is typically found in older designs and would often introduce its own set of vulnerabilities and overheads or require larger components. Specifically, the current source itself is composed of 32 PMOS slices, with typically 16 of them turned on during nominal operation to meet the AES's power demands.
Okay, so a cascade current source sounds very precise. Can you give us a slightly simpler analogy for what it does here? Almost like a highly refined faucet that maintains constant pressure no matter what's happening downstream, even if the pipes below it are constantly opening and closing.
That's a great way to think about it. Imagine that faucet. The cascade current source acts like an incredibly sophisticated self-adjusting valve. No matter how much the AES engine, the downstream pipes that open and close as it computes, tries to draw varying amounts of current, this cascade source works diligently to ensure the total current it supplies to the AES, and thus draws from the chip's external supply, remains almost perfectly steady. It effectively isolates the AES's internal fluctuating power demands from the outside world.
Isolates it. Got it. And there's a control system managing this.
Yes. To manage this intricate current source, the system employs a slow digital switched mode control, SMC, low dropout, LDO regulator. An LDO regulator is a type of linear voltage regulator that can operate with a very small input-output differential voltage. Its primary role here is to accurately track and precisely regulate the voltage across the AES engine itself, which they refer to as VDIG. It keeps this voltage within a tightly controlled target range, specifically between V-target plus A plus and V-target. It achieves this by digitally turning on or off the appropriate number of those 32 PMOS slices within the current source.
Okay.
Now, what's absolutely crucial here for the security aspect is a very specific design choice. The carefully chosen unit current, which is approximately 94 microamps. This unit current is deliberately set to be higher than the typical key-dependent variation in the average AES current, which is around 72 at total.
Higher than the variation. Why is that important?
This clever design ensures that any key-dependent information, any of those subtle whispers in the average DC current, is not transferred to the chip's external supply current. Instead, that sensitive information is effectively leaked, or maybe absorbed is a better word, and harmlessly absorbed by that bleed PMOS path to ground. This makes the entire design highly secure because no external observer can detect those variations.
So it's like a secret compartment or a drain where the whispers go to die internally, never reaching the outside world. And to ensure I'm grasping the key mechanism is the main point that the system is constantly making tiny, intelligent adjustments internally, so the outside world just sees a perfectly flat line without it introducing its own problems or noise.
Exactly. It's a self-regulating internal mechanism designed for precision. And beyond that, the SMC loop is incredibly robust. It's designed to handle process, voltage, and temperature, PVT variations, those natural inconsistencies that arise from manufacturing differences, varying supply voltages, and different operating temperatures that occur from chip to chip.
So it works reliably across different conditions.
Yes, ensures consistent performance and security. At startup, the CDSA requires less than 500 microseconds to settle, which can be accomplished during non-sensitive dummy operations before any real encryption begins, so it doesn't impact critical operation time. It's also important to note that the SMC LDO operates as a low bandwidth loop, clocked at less than 10 kHz, with the VDIG output pole at approximately 106 kHz. It also features a 50 mV deadband. This means it intelligently remains disengaged during the steady-state secure operation of the CDSA AES circuit.
Disengaged? Why?
To prevent it from introducing any new noise or potential leakage pathways during the critical encryption phase, it does its job setting things up, then stays quiet. The precise regulation is managed by two dynamic comparators that continuously monitor VDIG against its upper and lower target thresholds, and a 32-bit up-down counter with averaging controls the current source slices, meticulously maintaining that precise, unvarying supply current.
That's a lot of clever engineering at work to keep that current constant internally. But still, how exactly do they achieve that remarkable 350x attenuation of the current fluctuations at the supply? That number is just astonishing. It sounds like they're practically making the fluctuations disappear.
This is truly a key departure from how traditional series LDOs operate, where the supply current often closely tracks the load current. In CDSA, this tracking is deliberately avoided. Instead, the design tolerates a small, controlled 30 to 50 mV voltage droop across the AES engine itself. This VDIG voltage is carefully guard-banded to ensure no performance degradation for the AES, albeit at the cost of some minimal power overhead. The real magic happens because the high-impedance cascade current source with an incredibly high output resistance, that's 10K, sits directly on top of the AES engine. This configuration ensures that any current fluctuation generated by the AES at the supply is heavily attenuated. Essentially, the combination of the AES operating frequency, the bypass capacitance CL, and that high output resistance works together to squash those fluctuations. This results in that impressive 350 base suppression.
So the high impedance acts like a choke, Just squashing those fluctuations before they can escape, almost like putting a sound muffler on an engine.
Precisely. A very effective muffler. And the design ingenuity goes even deeper to maximize this effect. They use a cascode current source biased in subthreshold saturation. This specific biasing technique is vital because it significantly increases the output resistance ARDS by approximately 10 times compared to a simpler one-stack current source.
10 times higher resistance.
Yes. This, in turn, allows for a tenfold reduction in the bypass capacitance, CL, needed across the crypto engine, requiring only 150 PF for the same impressive attenuation level. Crucially, this capacitance, CL, is implemented using MOS capacitors, metal oxide semiconductor capacitors, integrated directly into the chip structure in lower metal layers of the chip, rather than using the larger, more exposed metal insulator metal lithium capacitors, typically found in top metal layer.
The lower metal layers again. That helps with EM too, right?
Exactly. This design choice further minimizes EM radiation, as lower metal layers are naturally less efficient at radiating signals due to their smaller physical dimensions. Both the shunt path PMOS bias and the number of PMOS legs turned on are also scan controllable, which aids in analyzing the effect of that extra bleed current on signature attenuation, as detailed in Figure 27.3.3. It's a very comprehensive, multi-layered approach to creating this profound silence from the chip.
We've spent a lot of time talking about power leakage, how the chip's power draw can inadvertently betray secrets. But electromagnetic signals, those invisible radio waves emanating from the chip, are also a major concern for secret key extraction, aren't they? It feels even more ethereal, harder to pinpoint and hide.
Absolutely, and it's a critical, often underestimated distinction. The paper highlights that EM leakage isn't just some vague byproduct, it's a strong function of the physical dimensions of the metal traces carrying the correlated current within the chip. Imagine these metal traces as tiny microscopic antennas. The larger the metal structures, especially those in the higher layers of the chip, the more efficiently they act like these tiny antennas. They can radiate key correlated signatures far more effectively into the surrounding environment, making them prime targets for EM side-channel attacks that can be picked up by sensitive receivers even from a distance. This understanding of the physics of EM leakage was rigorously validated through sophisticated 3D finite element method, or FEM, simulations of the metal traces, confirming how different trace geometries affect radiation.
So if these metal traces are like tiny antennas broadcasting sensitive information, how do they physically hide them or prevent them from broadcasting those secrets? It sounds like you have to almost sculpt the chip itself, not just design the circuits.
That's a brilliant way to put it. It is indeed about sculpting the chip's physical layout, working in concert with the circuit design. This is another incredibly clever aspect of their design, demonstrating a truly holistic approach to security that integrates physical layout with circuit countermeasures. To provide high EM SCA resilience, both the protected AES engine and the embedding CDSA circuit are locally routed, using lower metal layers within the chip, specifically up to M6.
Staying low down in the chip structure.
Exactly. This design choice is absolutely critical because it significantly suppresses any local correlated EM leakage before the attenuated and now almost constant current signature passes through to the top-level, larger metal layers of the chip or the board. By confining the sensitive fluctuating currents that still carry some key correlated information to these lower, physically smaller metal layers, they effectively silence the EM whispers right at their source, drastically reducing the broadcast strength.
And is there a quantifiable impact to this strategic routing? Does simply placing wires in a different part of the chip really make that much of a difference?
It absolutely does, and it's a significant factor. The paper details that this lower metal routing alone provides a local attenuation of approximately 6/8. This is a substantial improvement compared to letting the correlated signature pass directly through higher metal layers like M9, which have larger dimensions and thus radiate much more efficiently. It's a testament to how even seemingly small physical design choices, meticulously engineered, can have a massive impact on the overall security posture of the chip. This synergy between circuit design and physical layout is what makes CDSA so robust against both power and EM side channels.
The paper mentions different modes for testing the chip, almost like they built in different experimental setups right onto the silicon. What exactly were they trying to learn or prove from these different configurations, and what was the biggest challenge in making a chip so flexible for testing?
That's a great observation about their research methodology. The test chip was designed with incredible flexibility, precisely to isolate and analyze different aspects of security performance, allowing them to precisely measure the effectiveness of each countermeasure. They implemented three main design modes. Mode 1 was the unprotected AES implementation. This served as their crucial baseline for comparison.
The control group, basically.
Exactly, showing what an attacker could achieve against a standard unsecured design. Mode 2 was a setup that was power protected by CDSA, but was intentionally EM unprotected
Why do that?
to isolate the EM effect. They achieved this by using highly isolating switches SW2 to SW4, as depicted in Figure 27.3.2, to connect the VDIG node, the voltage across the AES, to higher metal radiating structures, specifically metal layers M7 through M9. This allowed them to specifically analyze and quantify the isolated effect of different metal layers on EM leakage, experimentally proving the hypothesis that higher layers radiate more. And Mode 3 was the default fully protected mode. In this mode, both power and EM protection were active, utilizing the full CDSA circuit combined with the strategic lower metal routing strategy.
So they could switch between different levels of protection to really pinpoint where the security was coming from and how effective each part of the solution was? It sounds like designing such a flexible test chip would be a significant engineering challenge in itself.
Exactly. This granular control allowed them to dissect the contributions of each countermeasure and understand the physics at play. The biggest challenge in designing such a flexible test chip, beyond the CDSA itself, was probably ensuring that these test connections themselves didn't inadvertently introduce new leakage paths or interfere with the core functionality. The design also includes scan-controlled, highly isolating switches, like SW1 in Figure 27.3.1, which could connect the VDIG node to an external pin. This was critical for observability during testing and debugging when SW1 was on-in. But during normal, secure operations, it ensures that this connection is completely disconnected without leaking any EM signals, maintaining the chip's secrecy. It's a very clever way to facilitate both rigorous scientific testing and robust, secure deployment.
This all sounds incredibly sophisticated in its engineering and design, but what do the numbers actually tell us about the real-world security achieved? How do they quantify something as significant as unprecedented protection?
To truly understand the profound impact of this research, we need to look at two critical industry-standard metrics used in hardware security. First, minimum traces to disclosure, or MTD.
Right, the number of observations needed.
Exactly. It's essentially the gold standard for measuring side-channel attack resistance. A higher MTD value means the system is significantly more secure, requiring exponentially more effort, time, and computational resources from an attacker, often to the point of making a practical attack completely infeasible. Second, test vector leakage assessment, or TVLA. TVLA is a powerful statistical method used to determine if a device is leaking information that correlates with sensitive data, such as a secret key. It calculates a t-value. A higher t-value indicates a stronger, more detectable leakage.
So high MTD is good, low t-value is good.
Precisely. All the impressive results we're about to discuss were obtained using a standard SCA attack setup involving an oscilloscope and a PC, as illustrated in Figure 27.3.S1, so these are very realistic measurements reflective of real-world attack scenarios.
Let's start with the power leakage, which is often the most direct whisper an attacker tries to detect. How did the CDSA-protected AES perform against conventional power attacks compared to the unprotected baseline?
The results here are truly remarkable. For the unprotected AES implementation, our baseline, a correlational power attack, or CPA, yielded an MTD of just 8,000 traces.
8,000? That sounds low.
It is very low. To put that in perspective, a determined attacker could likely extract the key after observing a mere 8,000 cryptographic operations. That's a very quick and practical attack to execute. In stark contrast, the CDSA AES remained completely protected even after observing an astonishing 1 billion 1B traces. This means the attack simply failed to reveal the key, even with an astronomical amount of data.
A billion traces compared to 8,000. That's an extraordinary difference. It really puts into perspective the scale of protection achieved. But for a truly determined state-sponsored attacker, is any system ever truly unbreakable, or does this just raise the bar to a practically infeasible level?
That's an excellent critical question. While no system can claim absolute unbreakability against unlimited resources and time, this represents an MTD improvement of approximately 125,000 times over the unprotected version.
125,000 times harder.
Yes. To truly put that into perspective for you, an attacker would need to gather data for 125,000 times longer than they would for an unprotected chip. This effectively moves the challenge from practically achievable to practically impossible for the known side-channel attack methods. Furthermore, a fixed versus random TVLA on the unprotected AES showed a t-value of 1056 after 200 million traces, indicating highly significant leakage. The CDSA AES, however, exhibited a t-value of only 12 under the same conditions.
Much, much lower leakage detected.
Dramatically lower. They even tried frequency domain CPA, sweeping the center frequency from 10 MHz to 1 GHz, but still failed to reveal the correct key byte after 1 billion traces, further confirming this massive improvement in power side-channel resilience. It's a game changer because it pushes the attack window so far out that it becomes economically and technologically unviable for most adversaries.
And what about those electromagnetic whispers, the signals radiating invisibly from the chip? Was the protection as robust there, or is EM leakage a harder beast to tame than power fluctuations?
It was equally impressive, demonstrating that CDSA tackles both vulnerabilities comprehensively and effectively. A correlation electromagnetic attack, or CEMA, on the unprotected AES revealed an MTD of approximately 12,000 traces.
Slightly higher than power, but still quite low.
Still very vulnerable, yes. Yet again, the CDSA AES was not broken even after 1 billion measurements, as clearly shown in Figure 27.3.5. This shows an equally robust defense against electromagnetic eavesdropping, silencing those radiating signals just as effectively as the power fluctuations.
Incredible. And what about the TVLA for EM? Did that tell a similar story of dramatically reduced leakage?
Absolutely. The TVLA for EM leakage on the unprotected AES showed a very high T-value of 961, indicating strong detectable electromagnetic whispers. The CDSA AES, in its fully protected Mode 3 with lower metal routing, achieved a significantly lower T-value of just 5.1.
Wow, 961 down to 5.1. That's huge suppression.
Truly remarkable suppression. What's particularly unique and insightful about this paper is how they explicitly demonstrated the crucial effect of metal routing on EM leakage using those modes we talked about. In Mode 2, where VDIG was intentionally connected to higher metal radiating structures, M7, M9, the EM leakage crossed the attack threshold, a statistical value of 4.5 within a mere 20 million traces. Compare this to Mode 3, the default protected mode with lower metal routing, which took approximately 170 million traces to reach the same threshold.
So roughly 9 times longer just because of the wiring placement?
Well, they state a local attenuation of over 7 times, but yes, a very significant difference purely due to routing. It highlights this crucial significance of routing sensitive current paths in lower metal layers for robust EM SEA protection. It's not just about the clever circuit, it's about the intelligent physical layout of the chip working in concert.
So the numbers don't lie. This isn't just an incremental improvement over existing solutions. This truly represents a monumental leap forward in hardware security.
Indeed. The CDSA AES achieves a monumental 100 times higher MTD compared to previous state-of-the-art countermeasures, moving from prior results of around 10 million traces to over 1 billion. This translates to a staggering 125,000 times MTD improvement for power attacks and an 83,333 times improvement for EM attacks, all compared to an unprotected implementation. These aren't just large numbers. They fundamentally shift the landscape of what's practically achievable for an adversary against hardware-based cryptography. This truly represents a new benchmark in physical security for cryptographic circuits, making them practically impregnable to known side-channel attacks by pushing the required attack effort into the realm of the unfeasible.
Often when we hear about such advanced, game-changing security, there's usually a catch, right? It typically comes at a significant cost in terms of performance, or it makes the chip much larger, it draws a lot more power. So is this CDSA technology practical for real-world deployment, or is it a brilliant but niche lab curiosity, too expensive or too slow to use widely?
That's a crucial question, as many past countermeasures indeed introduced significant trade-offs that severely hindered their widespread adoption. What's truly remarkable and makes CDSA AES a game-changer is that it achieves this unprecedented security without any performance overhead.
No slowdown at all.
None reported. The AES 256 implementation still runs at a brisk clock frequency of 50 MHz and requires just 14 cycles per encryption, maintaining its high throughput and speed, which is critical for real-time applications. Furthermore, the paper clearly states that the power and active area overheads are comparable to existing solutions.
Comparable, so it doesn't cost much more silicon space or battery life.
Apparently not significantly more than other countermeasures, which is impressive given the security boost. Unlike earlier methods that often relied on large embedded passives like capacitors and inductors, causing significant area and power penalties, CDSA offers dramatically superior security without sacrificing speed or requiring a vastly larger silicon footprint. This crucial balance of security, performance, and efficiency is detailed in their comprehensive overhead analysis and comparison with state-of-the-art countermeasures, as shown in Figure 27.3.6. This practicality means it's not just a lab marvel, but a genuinely deployable technology.
So what does this innovation truly mean for you, the listener, beyond the technical specs? Where might we see this technology making a tangible difference in our daily lives, securing our future against these invisible threats?
Zooming out, this kind of innovation pushes the absolute frontier of trust in our increasingly digital world. This technology has profound implications for virtually any application, where cryptographic keys are processed on a physical chip and are currently vulnerable to side-channel attacks. Think about the devices you interact with every day. We could see CDSA implemented in the secure elements found in the smartphones you carry, protecting your biometrics and payment information.
Like the chip in my phone's secure enclave.
Potentially, yes. And in the smart cards you use for public transport or banking. It could secure the hardware security modules, or HSMs, that safeguard massive amounts of sensitive data in cloud infrastructure, forming a more resilient backbone for online services.
Okay, so core infrastructure too.
Definitely. Consider the rapidly expanding universe of IoT devices, from smart home gadgets to industrial sensors, monitoring critical infrastructure where battery life and cost are paramount. CDSA's low overhead and high security make it ideal for these power-constrained distributed systems, ensuring their communications remain truly private and tamper-proof. And crucially, it could secure critical automotive electronics. Imagine a scenario where a compromised automotive chip could allow an attacker to remotely eavesdrop on vehicle data, or even inject commands, purely by observing its EM emissions.
That's a scary thought.
It is. This technology effectively closes that door, making the car's internal communications truly private and secure, a matter of both data integrity and physical safety. This isn't just about protecting passwords, it's about building a fundamentally more resilient, trustworthy foundation for all our secure communications and critical systems, ensuring that our digital secrets remain truly secret, even against the most sophisticated physical adversaries. This really raises the bar for hardware designers, forcing them to consider physical security from the ground up in a way that's now demonstrably achievable and practical.
What an incredible deep dive into making our digital secrets truly hidden, even from the physical whispers and emanations of our devices. It's truly fascinating to see how clever circuit design, combined with thoughtful physical layout, can transform the security landscape, taking us from easily compromised keys with a few thousand observations to virtually unbreakable ones with the CDSA approach. It's a remarkable testament to human ingenuity and the relentless pursuit of robust security.
Indeed. This groundbreaking work by Das and the collaborative team highlights the continuous innovation required to stay not just abreast, but significantly ahead of sophisticated adversaries. It powerfully demonstrates that by deeply understanding the fundamental physical principles of information leakage, not just the digital ones, we can engineer solutions that were once thought impossible, building robust, resilient defenses right into the silicon itself, at the very heart of our technology.
To recap, we've explored how current domain signature attenuation dramatically reduces both power and electromagnetic leakage from encryption chips, achieving over 1 billion traces to disclosure. That's an improvement of over 100,000 times compared to unprotected versions, all without slowing down the chip or adding significant cost. It's a true advancement for hardware security. So as you go about your day, think about all the devices silently protecting your data. This deep dive shows that sometimes the most robust security isn't about stronger, more complex locks. It's about making the secret so quiet, so perfectly attenuated, that it's virtually indistinguishable from silence itself. What other invisible threats might we be overlooking in our increasingly connected world, and how might similar fundamental insights unveil their solutions? We'd love to hear your thoughts on this, what stands out to you. You can find us at podcast, website, social media to continue the conversation.